State Kirchhoff's second law. Kirchhoff's second law gives you the information about the conservation of energy, right? Conservation of energy. Conservation of energy in an electrical circuit states that the sum of the EMFs of the battery should be exactly equal to the sum of the potential differences across the components around a complete circuit or around a complete loop, which just makes sure that the energy is conserved, right? So that there is no loss in EMF, so that there is no energy being destroyed or being created around a closed loop of a circuit. So it states that sum of EMF is equal to sum of potential difference around a complete loop of circuit. Next, a battery of electromotive force 5.6 volts and the internal resistance R is connected to two external resistors. So here we have this figure. The two external resistors are connected in parallel. This is the battery and it's connected, it has some internal resistance to it. The voltmeter is attached at these two ends and the reading is 4.8 volts on the voltmeter. Calculate the combined resistance of the two resistors connected in parallel. So that's pretty straightforward, right? The combined resistance of parallel combination is the inverse addition of resistors. So this gives you the resistance equivalent as 1 by 90 plus 1 by 18 ohms inversed. So this is about 15 ohms. Next, we want to compute the current in the battery. The current in the battery, it can be computed from Ohm's law as V equals IR. V is the potential drop across the resistor the resistor R. So this is I equals V by R, and the potential drop is measured as 4.8 volts across these two ends. So these two ends means that it's the same thing as connecting the voltmeter across these two, or you can say that the potential drop across the two parallel resistors would be exactly the potential drop that is observed on this one, which is 4.8 volts. So this is 4.8 volts divided by the total equivalent resistor, which is 15 ohm. So this gives you a current of 0.32 amperes. Now show that the internal resistance is 2.5. So we use Kirchhoff's second law. According to that, the total EMF is equal to the potential drop across the two resistors, the entire circuit, plus the potential drop across the internal resistance, which is I times small r, which is just IR plus I times small r, or I times R plus R, which just gives you the value of R from this thing you have to compute. So this would be E minus I times R divided by I. So you just put in the values now. The EMF, which is 5.6 minus 0.32 times R, which is 15, divided by 0.32. This gives you the internal resistance of 2.5 ohms. Determine the ratio power dissipated by internal resistance R divided by total power produced by the battery. So the power dissipated is by the internal resistance R is just the power, the current that passes through the internal resistance, right? I squared R. And the total power produced by the battery is V times I, where V is the EMF of the battery, so let's call it E times I. So the power dissipated, I squared R, is just 0.32 squared into the internal resistance, which was 2.5 ohms. This is the power dissipated, and the total power, which is EI, is the EMF of the battery, which was 5.6 times 0.32, which is the current. So the ratio of the two is I squared R over EI, and that's 0.32 squared times 2.5 divided by 5.6 into 0.32. So 0.32 gets with this squared cancelled, and this gives you 0.14. Next, the battery in B is now connected to a battery of EMF 7.2 volts. So this battery is connected to another battery, and there is an internal resistance of the second one as 3.5 ohms. The new circuit is shown. Determine the current in the circuit. So the current in the circuit can be determined by writing an equation for this circuit as, so we start from 7.2 EMF. So the sum of the EMFs should be equal to the total the total sum of the EMF in this circuit should be equal to 0. So this should be 7.2 from this. Then you go here and you get to this one, which is now minus 5.6 as you're coming to the same terminals, and then minus the internal resistors, which is 2.5 times I minus 3.5 times I, the potential drop coming from the internal resistance, and this should be equal to 0. Next, you can just rearrange this equation for I to get 0.27 amperes.